Good evening to all of you. Good evening to all of you. I hope my voice is clear to all of you. Good evening to all of you. Welcome to Gate Wallah. So as this is the first class in this crash course series, so regarding this, almost 6 to 7 topic I am going to teach you. Every day 1.5 hour, some day 1 hour. So the length of the topic will be around 1 hour and sometime 1.5 hour, adding the numerical part. So theoretical plus numerical both type of discussion will be there in the class. Every day one topic we'll discuss in detail up to not only gate level, even for ESC level also. That means I'm going to teach you the derivation part also. Related to that, if you are having any doubt, we can discuss that on our Telegram group. So if you have any doubt or query related to this session, you can discuss like after class, after the live class gets over, you can discuss that part in the Telegram group also. So let's start discussing about the topic. So today as we are starting, I'm starting with a topic which is Stokes Law. And in Stokes Law also, specifically I'm talking about terminal settling velocity in plain sedimentation tank. So before starting the Stokes Law, let's give a small intro about the plain sedimentation tank. As you all know this, in the water treatment, the first unit operation what we are going to give, that unit operation is the plain sedimentation. Now here I am using a word unit operation. Here I am using the word unit operation. What's the difference between unit operation and the unit process? That is the first question which comes in your mind. Whenever you are using some physical forces to remove the pollutant, that is something what we are calling it as, that is something which we are calling it as Dark Knight, whatever you have doubt related to the batches and all, that we can discuss later on, like after the class. Right now, just listen the concept part, which like for that I am here. Okay, so it is only 1 hour class. So any general discussion I don't want right now. Do this type of discussion you can do it in the Telegram. For that we have a Telegram group. There you can message me. Okay. Now, what I was discussing about unit operation and unit process. Unit operation and unit process. Now unit process, here you are removing the pollutant by using some chemical forces and biological forces. So by this meaning what happens, the unit process will be a irreversible process. But unit operation will be a reversible process. Example for you, this plain sedimentation unit. It is a unit operation. Here what you are doing it, you are removing the suspended particle, mainly suspended particle. Why you are able to remove the suspended particle in this tank with the help of plain sedimentation tank? Why you are able to do? Because this suspended particle is having a specific gravity slightly greater than 1. Slightly greater than 1. So if any particles who is having specific gravity more than 1, that particle will have a natural tendency to get settled down at the bottom. Yes or no? But why these particles, why these suspended particles are not settling without plain sedimentation tank? Like normally why these particles are not settling? Because two things which is actually disturbing it. One is the flow turbulence. In that flow we have some turbulence, and the flow velocity. Because of these two things, these particles are not able to settle down. Now in this plain sedimentation tank, we are actually providing these two things in a best possible way. What we are saying it, in a plain sedimentation tank, we are making the flow turbulence and this flow velocity in a control manner. See, then you will say, sir, why can't you make these things 0? You can make it. That is what the batch reactor is, your batch settling unit is. But if you are using a batch reactor, you will be unable to fulfill the demand of the whole city. So we are compromising little bit with the quality, but we have to manage with the quantity na, each and every day, that too on the same time. So for that reason, what we have done it, instead of making complete zero for the flow turbulence and flow velocity, we are compromising with, we are just controlling the flow velocity and the flow turbulence. So in a plain sedimentation tank, we are controlling the flow velocity and the flow turbulence. Because of that, the particles will settle down. Which particle I am talking about? Suspended particles I am talking about. Now, if those particles are settled down at the bottom, here 2 points or 2 small concept which is very keyword I will say, which is very important for you to understand. One is settling, another is sedimentation. See, settling process do not require sedimentation. Sedimentation means settling at, like getting sedimented at the bottom. But sedimentation requires settling of the particle. For sedimentation to take place, the settling of particle is something which is required for you. Okay, so that's the difference between settling and sedimentation. Just to give an example, like if I will throw you from like 10th floor or 9th floor, if I will throw something, while moving from 10th floor to 9th floor or ground floor till it reaches the ground floor, that movement, that going down is basically called as settling. Once you landed at the ground, now that is the sedimentation. Same thing for the particles. Same thing for the particles. Okay. Now here in this plain sedimentation tank, we are seeing it type 1 settling. What this type 1 settling is, this is something which we are also calling it as discrete settling. Discrete settling. This is something what we are also calling it as discrete settling. Now what this discrete settling is? Discrete settling is basically type of settling where during the course of settlement, the particles do not change their mass, shape, specific gravity. They are not changing their mass, shape and specific gravity. That type of settling we are calling it as discrete settling. Neither they will change their mass, shape nor specific gravity, nothing will change. So separately, discrete means separately they are settling it. So that type of settling we are seeing it in the plain sedimentation. Now the next question arises, sir, that settling velocity, if you talk about settling velocity of the particle, what type of settling velocity you are considering it? Generally, in a normal way, if you see a particle is going from top to bottom, basically the G will be applied, acceleration due to gravity, and because of that, the particle will be in an acceleration mode. But taking that part into the consideration, it is very difficult for again analyze this situation. So what we are saying it here in this type 1 settling, here particle settles with terminal settling velocity, and there is the concept which we have to discuss. That is the topic of the day. We need to discuss the terminal settling velocity. So this was just an introduction for all of you so that you all come to a same level. Here the particles settle with a terminal settling velocity. Now this terminal settling velocity, especially the terminal velocity, this is a term which is actually from the fluid mechanics chapter is boundary layer theory. There means this term is actually associated with the fluid mechanics. What this term is, this term tells you any particle, like this particle if you talk about, this is the particle. Any particle which is experiencing 3 force, it is going down, so obvious thing will be the drag force will be upward. As these particles are going down, so drag force will be upward, weight of the particle will be acting downward. At the same time, the buoyant force will be acting upward. So when the weight of the particle, submerged weight I am talking about, if that becomes equal to the drag force, At that point, whatever the velocity will be, that is what we are calling it as terminal settling velocity. And now below that, the particle will go with the same velocity. Just to give you an example, you can take an example of a raindrop. Now if you see the raindrop, when it actually come out from the cloud, at that time the speed is 0. But as it is falling v equal to u plus at, even though u is 0, but it is having an acceleration due to gravity now, which is z 9.81 meter per second square. Now because of that, as it is coming down, the velocity is increasing. As the particle velocity will increase while going down, drag force will also increase, because drag force is a directly proportional to the relative velocity of square of relative velocity. So if you increase the velocity of the particle, in that case the drag force will also increase. A time will come when this drag force will be equal to the weight. That moment, whatever the velocity is achieved by the particle, whether it's a raindrop or this particle, that velocity we are calling it as terminal settling velocity. After that, with the same velocity, the particle will go down. After that, with that same velocity, the particle will go down. Now, this is what the terminal settling velocity is. Terminal settling velocities. So, I'm asking to all of you in the chat section, this terminal settling velocity, is that clear to all of you? The terminal settling velocity, is that clear to all of you? The terminal settling velocity, is that clear to all of you, my dear? The term. Remaining thing we'll discuss now, but I'm just asking about the term. Is that term is clear to all of you? Terminal settling velocity. Clear? Okay. Now, for our situation, which is basically particles are settling in a plain sedimentation tank, here, for the terminal settling velocity, we are actually following the Stokes law. We are actually following the Stokes law. Stokes law. In the Stokes law, two assumptions, which is actually Stokes has suggested two assumptions. So first write these two assumptions. The first assumption what Stokes has suggested, that all particles are settling with terminal settling velocity. All particles are settling with terminal settling velocity. सारे पार्टिकल जो हैं वो टर्मिनल सेटलिंग वेलोसिटी से सेटल कर रहे हैं. All particles are settling with terminal settling velocity. With terminal settling velocity. Now tell me, is it really gonna possible for you? No, because the depth of the water tank is not that much large. It is not that much large depth, so that you will be able to achieve the terminal settling velocity. No. So actually this will not happen. But this is the assumption what we have taken while giving the Stokes law. Second assumption what Stokes has taken, all particles are in spherical shape. All particles are in spherical shape. So all the particles here, now you also know that in a water, all the suspended particle will not be in a spherical shape. But this is the assumption what we have taken. This is the assumption what we have taken. So this is the two assumption that we have taken in the Stokes law. Now, as I said, it is following the terminal settling velocity. So if you want to derive it, the condition, at terminal settling velocity, at terminal settling velocity, you know that the drag force will be equal to W minus FB. This is something what we are calling it as submerged weight. Drag force formula is something known to you, half into CD into rho into area into, it is moving with a velocity V, so I'm using, Vs, so I'm using that Vs square equal to. Now what about weight? Weight is something specific weight into volume of the body, minus what about buoyant force? It is gamma W into volume of the body. Am I right? No issue. Buoyant force formula, you already know it. Now half into CD into rho area. For the drag force, the area will be, if you consider the diameter of this as D, so area, the drag force area which we are considering it will be pi by 4D square into Vs square equal to, here you can take Vb common, so it will be 4 by 3 pi r cube. So r in place of r, I am writing d by 2 cube. In bracket you have gamma s minus gamma w. I don't think so anybody will have any issue in this part. Is that clear to all of you till here? Is that clear to all of you? Now my priority is to find out Vs square. So my priority is to find out settling velocity. So I will focus on that only. So if you write Vs square, the remaining thing I will put in the right side. Pi and pi will get cancelled out. This is 1 by 4. So 8 by 3, 8 into 32 by 3. Is it right? 4 into 2, 8. 8 in that side, it will be 32. So 32 by 3. Pi and pi is already cancelled. CD will be at the bottom. Then you have rho. Rho will be nothing but, here you are considering water. So rho W it will be. That also you have to keep at the bottom. This will be d cube. Not d cube. This side we have d square, this side d cube. So only d. 1 by 2 to the power cube, 1 by 8. So that I am writing at bottom. Clear? 4 is 16. 16 into 2, 32. So that is clear to you. In bracket you have gamma s minus gamma w. Without any doubt. Without any doubt. I'm using this equation. I'm taking to the next slide. Taking an extra slide for this. Vs square. It will be 4 by 3. 4 by 3 CD into D into this gamma s minus gamma w. I can take G common. So this will become rho s minus rho w divided by rho w. I'm writing it. So the equation I got, Vs square is equal to 4 by 3 CD into GD into, this will be G minus 1. Rho s upon rho w is specific gravity, so I'm writing G minus 1. That means the formula for Vs what we got, 4 by 3 CD GD G minus 1. This is the formula for the settling velocity. This is the general formula for the settling velocity that we got. General formula for the settling velocity. This is CD, capital C, and then D. Coefficient of drag. Coefficient of drag. Where CD is the coefficient of drag, D is the diameter of the particle, G is the specific gravity of the particle. Specific gravity of the particles. Clear? Now, for the coefficient of drag, we have different value, like we have 24 upon Re. This is for laminar flow, where Re is less than 1 for laminar flow condition. CD will be equal to 24 upon Re plus 3 upon root under Re plus 0.34 when Re is greater than 1 but less than 10 to the power 4. CD is equal to 0.4 when Re is greater than 10 to the power 4. Re is greater than 10 to the power 4. Clear? Now, you want to find out for laminar flow. So for laminar flow, if you want to find out the formula for settling velocity, for laminar flow, condition is CD will be equal to 24 upon Re. So 24 upon Re is basically what? It is rho Vd by mu. Here we are taking it as Vs. So let us put this into the Vs formula. So Vs square is 4 by 3 CD. D we have 24 and the rest thing will go on the top. So 24 mu into rho into Vs into D. Already we have D into G bracket में Z minus 1. In bracket we have Z minus 1. So Vs and Vs will get cancelled out. So you will have Vs equal to 4. This will be ZD square upon 18 mu. So mu divided by rho. So it will be nu actually. Okay. In bracket you are having G minus 1. So this is the formula for the settling velocity for laminar flow. And also in terms of diameter, if you talk about less than 10 to the power minus 1 mm, generally what happens if your diameter of particles is very less, then only there will be a chance of laminar flow creation. Otherwise, if the diameter of the particles are very large, in that case, mostly the flow will be turbulent flow. So D less than 10 to the power minus 1 mm, that is something what we are calling it as laminar flow. Is that clear? Is that clear to all of you? Now here one new term, which is the kinematic viscosity. Kinematic viscosity, the unit we are going to use it as SI unit will be meter square per second. In CGS, it will be centimeter square per second. Centimeter square per second, we are also calling it as Stokes. So all these are units of kinematic viscosity. Mu is nothing but the dynamic viscosity. So it will be Newton second per meter square or kg per meter second. Newton second per meter square or kg per meter second. Kg per meter second. I think battery is down. Let me change it. Battery is down. Let me change it. Bacha. Now it's okay now. So this is the formula for settling velocity, and this formula we are going to use it in many places. Even in grid chamber, we'll see this formula. Even though in grid chamber, sometime when they will give you the flow as a laminar, you will use this formula only. You will use this formula only. So this is the ultimate formula that we use it for the discrete flow. Wherever discrete flow is there, we'll use the Stokes law formula, Vs equal to Gd square upon 18 nu G minus 1. This is specially for laminar flow. General formula is this one. General formula is this one. Clear to all of you? By this logic, they will ask you, like by this derivation, they will ask you one more question. What are the factors on which the settling velocity depends? Factor on which terminal settling velocity depends. The first factor will be the D. So terminal settling velocity is directly proportional to diameter, or it's better to write directly proportional to square of the diameter. Then inversely proportional to inversely proportional to kinematic viscosity. Kinematic viscosity. Inversely proportional to kinematic viscosity. Then again directly proportional to specific gravity of the particles. Next, what about temperature? If you try to relate with the temperature, see, if you increase the temperature, the viscosity will increase or decrease? The viscosity will increase or decrease? Tell me. The terminal settling velocity, I want to see all of you in the chat section. The terminal settling velocity, how it is related to the temperature? How it is related to the temperature? Inversely or directly? Now, terminal settling velocity is directly proportional to temperature. What does it mean? It means if you increase the temperature, what will happen? If you increase the temperature, the viscosity will go down. For any general liquid, the viscosity will go down. I'm talking about liquid, not gases. So viscosity will go down. If viscosity will go down, Vs will increase, because nu and Vs are nothing but inversely proportional. Clear? So temperature actually increases the settling velocity. So in a hot water, you will find the particles settling fast compared to the cold water. So terminal settling velocity is directly proportional to temperature. That is what I'm writing it. Is that clear to all of you? Is this concept is clear to all of you? Now, here only I'm giving you another idea about the two velocity. One you have studied just now, which is settling velocity. The next velocity which I'm going to talk about, that is the V0. V0 is the one of the design property or design criteria in the plain sedimentation tank. V0 is something what we are calling it as overflow velocity, or another name will be surface loading rate, short form SLR. Or sometime we also call this as surface overflow rate, SOR. General symbol is V0, that is discharge upon, actually it's a plan area. We write it as a surface area, but actually it's a plan area. Like if it is a rectangular triangle, so if you have a base of base width is B and the length is L, so for a triangular section, Q upon L into B. If it is a circular section, so V0 will be Q upon pi by 4 into D square. Now you will say, sir, we are actually discussing settling velocity, terminal settling velocity. Why you are introducing me V0? What is the use of this now? Why I'm introducing this? Because I can tell you the application of settling velocity in your settling process, especially in a plain sedimentation case. What happens if your overflow velocity is more than the settling velocity of the particle? If your overflow velocity is more than the settling velocity of the particle, in that case, particles will not settle, particle will not settle in the plain sedimentation, or particle will not settle in the tank. Simple. If your Vs is more than or equal to V naught, in that case, the particles will settle in the tank. So for the particles, two velocity, one velocity it experiences, which is the overflow velocity, that is going upward, vertically upward. Settling velocity, that is vertically downward. In between these two velocity, whichever will win, accordingly the particle will react. If V naught will be more than Vs, in that case the particle will not settle in that tank. For that tank, if the Vs is greater than the V naught, in that case the particle will settle in the tank. Here remember, Vs is something which is dependent on the particles diameter and the liquid both. So it depends on the particles also, it depends on the liquid also, flow property also. But the V naught, as you have seen, Q upon surface area, Q is anyway for a constant for a design. So it only depends on the surface area, which is basically the tank property. So always remember, surface overflow rate is the tank property, and Vs is basically the particle related property or flow related property. So for a tank, in a particular tank, V naught will be constant. Different particle will be there, and for all the particle, as their settling, as their diameter are different, so their settling velocity will be accordingly, it will be different only. So that's why in the same tank, some particles get settled down, some particle do not. That's because their settling velocity is lesser than the V naught for the tank. If their settling velocity is more than the V naught, in that case, definitely that those particles will settle down at the bottom. Now this is the complete application of your settling velocity. This is the complete application of your settling velocity. With this, now the today's topic is over. If you have any doubt, if you need any discussion related to this, you can tell me quickly. If you have any doubt or any discussion, you can tell me quickly. So today what we have discussed a small intro about the plane sedimentation unit, what type of settling occur in that unit, discrete settling we have discussed. Then we talked about the terminal settling velocity, what this terminal settling velocity is. For that terminal settling velocity, we have used the Stokes law to find out the formula for that. In our plane sedimentation case, Stokes law basically based on the terminal settling velocity concept, which tells us the FD, the drag force, will be equal to the submerged weight, which is W minus FB. So FD equal to W minus FV, we had did it, and then we got the formula. For the Stokes law, we have also studied the assumption part, the two major assumption that is very important for you to remember. And then I have shown you some part of application. Stokes law or settling velocity is having many application, but one of the application which is there in the plane sedimentation unit, that's something I have shown it to you. So I hope this is completely clear to all of you. As this is the first day class, so that's why I'm putting it. If you are having any doubt or any discussion related to this topic, or any discussion related to the civil engineering exams, you can discuss with me here. It's not ID, it's a Telegram group for discussion. Mrigank, that is my name, sir, and the PW. This is a Telegram group. There you all can join for all the discussion related to civil engineering, or the subject which I am teaching right now, that is the environmental engineering, or any other subject which is fluid mechanics, hydraulic machine, any other subject which I am teaching it for you. Those subjects related discussion also you can do it here. Okay. Even any doubt in this today's class also, like maybe you are not watching it live, you are watching as a recorded, so you can ask that doubt, whichever doubt comes in your mind, in this group only. I will try to reply as quickly as possible to you. With that, today's class is up to this much only. Tomorrow topic, I can tell you, tomorrow topic which I am going to discuss, that will be the chlorination. So tomorrow topic will be the chlorination. Same timing, not same timing. Today we have started at 6:30, na? But from tomorrow onwards, we'll start at 6 p.m. sharply. 6 p.m. to 7:30. That is the time slot which is given to me. So I will start sharply at 6 p.m. Okay. I hope there is no one is having any query related to this topic. Still, if somebody who is watching as a recorded, you are free to ask doubt. This Telegram group which I told you, this is free for everyone, every aspirants. Okay, so bye bye, take care. We'll meet tomorrow again at same, not same timing, at 6 p.m. actually. Timing, I think it's better I will write it here so that you will not confuse about it. Timing will be 6 p.m. This timing slot I will use it for my lecture. Till 30th July, I'm going to take the classes on different topics, Monday to Friday. Monday to Friday. Saturday, Sunday, I will not take the class. So Monday to Friday, you will have the class at 6 p.m. to 7:30 p.m. At 6 p.m. to 7:30 p.m. Okay, all clear? Bye-bye, take care. Jai Hind.